So here's something that might seem a little strange to think about right now. Wherever you are, lying in the dark, getting comfortable, right at this very moment, there are invisible fields passing through your body. Not one or two, countless overlapping fields, crisscrossing the room, flowing through the walls, through the pillow under your head, through you. Radio waves from a station you've never listened to. The faint magnetic influence of the earth itself, gently tugging on every compass needle within 1,000 miles of you. The infrared warmth radiating off your own skin. The electric signals running down your nerves, telling your heart to beat. All of it, every single one of those things, is electromagnetism. One phenomenon, one set of rules. And for most of human history, nobody had the faintest idea any of it was connected. That's what makes this story so beautiful, honestly. Because electromagnetism isn't just some chapter in a physics textbook. It's the force that holds atoms together, the reason light exists, the principle behind every motor, every generator, every phone screen, every MRI machine, every lightning bolt. It's arguably the most important force in your daily life, way more than gravity, even though gravity gets all the credit. Gravity keeps you on the ground, sure, but electromagnetism is doing almost everything else. The chair you sat in today didn't collapse because of electromagnetic bonds between atoms in the wood or metal. You can see because electromagnetic waves hit your retina. Your brain works because of tiny electrical impulses. And yet, for thousands of years, people thought electricity and magnetism were completely separate, unrelated curiosities. Getting from that misunderstanding to the unified picture we have now, that's one of the great detective stories of science. And it starts in a place you might not expect. Let's go way back, like ancient Greece back, around 600 BCE, give or take. There's a philosopher named Thales of Miletus, and Thales was one of those rare people in the ancient world who tried to explain natural phenomena without invoking the gods. He wanted mechanical reasons, physical causes, and Thales noticed two strange things that, as far as he could tell, had nothing to do with each other. The first was this. If you took a piece of amber, which is fossilized tree resin, sort of a golden, translucent stone, and rubbed it against fur, it would attract small, light objects, little bits of straw, feathers, dust. You'd rub the amber, hold it near some chaff, and the chaff would jump toward it and cling. It was eerie. It seemed almost alive. And in fact, Thales reportedly suggested that amber must have a soul, because it could move things without touching them. Now, what he was actually observing was static electricity. The rubbing was transferring charge from the fur to the amber, creating an electric field. But of course, Thales had no framework for any of that. He just knew it was weird and wonderful. The second thing Thales noticed, and this is important, was lodestone. Lodestone is a naturally magnetized mineral, a form of magnetite, an iron oxide. You can find it in certain rocks, and it has this remarkable property. It attracts iron, just pulls it right in. And if you suspend a piece of lodestone from a string, it rotates to point roughly north-south. Again, Thales had no explanation. He just noted that lodestone, like amber, could exert force without contact. But here's the thing. He didn't connect them. To Thales, amber doing its trick and lodestone doing its trick were two separate mysteries. And that's how they stayed, in most people's minds, for over 2,000 years. Think about that for a second. 2,000 years. Electricity and magnetism sitting right next to each other in the catalog of strange natural phenomena, and nobody realized they were two faces of the same coin. That's not because people were foolish. It's because the connection is genuinely subtle. You can't see it just by watching. You need specific experiments, specific setups, and, honestly, you need a particular kind of luck. But let's not jump ahead. Let's stay in the ancient world for a moment, because there's something worth appreciating about how people understood these forces, or didn't, for most of history. The word electricity itself comes from the Greek word for amber, electron. That's how closely the phenomenon was tied to that one material. For centuries, static electricity was basically an amber trick, a party curiosity. You rub amber, things stick to it. Neat. Nobody saw any practical use for it, and nobody investigated it very deeply. Magnetism, on the other hand, actually did get some practical attention, mainly because of that compass property. The Chinese were using magnetic compasses for navigation as early as the 11th century, possibly earlier. Some evidence suggests rudimentary compass use going back to the Han Dynasty, around 200 BCE, though the details are debated. By the 1100s, Chinese navigators were definitely using magnetized needles floating on water to find north. The technology spread westward along trade routes, reaching Europe by the 12th century, and it transformed ocean navigation. Before the compass, sailing out of sight of land was terrifying and dangerous. You navigated by the stars, and if the sky was overcast for a few days, you were essentially lost. The compass changed that. It gave you a direction you could trust, even when you couldn't see the sky. But here's what's fascinating. Nobody understood why it worked. People knew that a magnetized needle pointed north. They knew that lodestones could magnetize iron by rubbing. They knew magnets had two ends, and that like ends repelled, while opposite ends attracted. But why? What was actually happening? That remained a complete mystery. There were theories, of course. Some medieval scholars thought lodestones were attracted to the North Star. Others thought there was a giant magnetic mountain at the North Pole. Some thought magnetism was a form of sympathy between substances, a kind of cosmic affinity. These ideas sound quaint now, but remember, these people had no concept of fields, no concept of charge, no atomic theory. They were working in the dark, almost literally. The first person to really take a serious, systematic, experimental look at magnetism was an Englishman named William Gilbert. And Gilbert is a genuinely interesting character. He was born in 1544 in Colchester, studied at Cambridge, became a physician, and eventually rose to become the personal doctor to Queen Elizabeth I. So he had status, he had resources, and he had a deeply curious mind. In 1600, he published a book called De Magnet, On the Magnet, and it's one of the most important scientific works of its era. What Gilbert did was simple but revolutionary. He actually tested things. He didn't just philosophize about magnetism. He built experiments. He carved a lodestone into a sphere. He called it a terrella, a little earth, and he moved a small compass needle around its surface, mapping out how the needle oriented at different positions. And what he found was remarkable. The compass needle behaved around his terrella exactly the way compass needles behave on the surface of the actual Earth. Near the equator of the sphere, the needle lay flat. Near the poles, it dipped vertically. This was, as far as Gilbert was concerned, proof that the Earth itself was a giant magnet. That's why compasses point north. Not because of a magnetic mountain or the North Star, but because the planet itself has magnetic poles. Now, Gilbert was right about that, and it was a huge insight. But he also did something else that's important for our story. he drew a clear distinction between magnetism and what he called the electric force, the amber effect. He experimented with static electricity too, and he found that it wasn't just amber that could attract things after being rubbed. Glass, sulfur, sealing wax, and various other materials could do it too. He coined the term electrics for materials that could be charged by friction. But, and this is crucial, Gilbert insisted that electricity and magnetism were fundamentally different phenomena. Magnetism, he said, was deep and cosmic, related to the Earth's very nature. Electricity was superficial, a minor surface effect caused by rubbing. He saw them as entirely separate. And you know what? Given what he could observe, that was a perfectly reasonable conclusion. With the tools available in 1600, there was no obvious connection between rubbing a piece of amber and the behavior of a compass needle. Gilbert was wrong, but he was wrong for understandable reasons. And his work set the stage for everything that came after, because he established that these phenomena deserved serious experimental investigation. He gave them scientific legitimacy. After Gilbert, the study of electricity slowly picked up momentum through the 1600s and 1700s. And this is where the story gets fun, because the early electrical experimenters were, let's be honest, kind of wild. This was the era of spectacular demonstrations, parlor tricks, and occasionally dangerous stunts, all in the name of understanding this mysterious, invisible force. One of the key developments came in 1745, when a Dutch scientist named Peter van Musschenbroek, working at the University of Leiden, accidentally invented one of the first devices that could store electric charge. He was trying to electrify water in a glass jar, and he got a tremendous shock when he touched the jar while it was connected to a friction generator. The device became known as the Leyden jar, and it was basically a glass jar coated inside and out with metal foil, with a metal rod sticking through the top. You could charge it up using a friction machine, and it would hold that charge until you provided a path for it to discharge, at which point it would release all its stored energy in a sudden, painful spark. The Leyden jar was a sensation. For the first time, you could accumulate a significant amount of electric charge and release it on command. People went absolutely wild with it. There are accounts of experimenters lining up dozens of people holding hands, then discharging a Leyden jar through the chain. Everyone would jump and yelp simultaneously, which was considered marvelous entertainment. In 1746, Jean-Antoine Nollet, a French physicist and showman, famously discharged a Leyden jar through a chain of 180 royal guards in front of King Louis XV. All 180 soldiers jumped at the same instant. The king was reportedly delighted. But beneath the showmanship, something important was happening. People were starting to take electricity seriously as a force of nature, something with real power, something that could be accumulated, stored, and directed. And one person in particular was about to push the understanding of electricity further than anyone had before, working not in a European university, but in a print shop in Philadelphia. Benjamin Franklin. Now, Franklin gets mythologized a lot. The kite in the thunderstorm, the key on the string, all of that. And some of the mythology is exaggerated or simplified. But Franklin's contributions to electrical science were genuinely profound, and they're worth slowing down for, because some of the concepts he introduced are ones you still use today, whether you realize it or not. Franklin started experimenting with electricity in the mid-1740s after seeing a demonstration of electrical tricks by a traveling lecturer. He got hold of some Leyden jars and a friction generator, and he threw himself into the subject with the same intense practical curiosity he brought to everything. And within a few years, he developed a theory of electricity that was remarkably clear and surprisingly modern in its structure. Here's what Franklin proposed. He said that electricity was a single fluid present in all matter. When you rubbed amber with fur, you weren't creating electricity. You were moving it. The amber gained an excess of this fluid, and the fur lost some. He called the condition of having excess fluid positive, and the condition of having a deficit negative. And this is where those terms come from: positive and negative, plus and minus. Franklin invented that convention, and we still use it today, everywhere, in every circuit diagram and every physics equation. When you see a plus sign on a battery terminal, that traces directly back to Benjamin Franklin's theory from the 1740s. Now, Franklin got one thing wrong, and it's a small irony that has confused physics students ever since. He guessed that the electrical fluid flowed from positive to negative, from the thing with excess to the thing with a deficit. That seemed logical. But when electrons were eventually discovered about 150 years later, it turned out they flow the other way, from negative to positive. So conventional current, the way we draw it in circuit diagrams, flows in the opposite direction from the actual movement of electrons. That's Franklin's legacy, a convention so deeply embedded that even after we discovered it was technically backwards, we just kept using it. Every electrical engineer in the world works with this slightly backwards convention every single day, and it's all because of a guess Franklin made in Philadelphia in the 1740s. He just picked the wrong direction, and by the time anyone could check, the convention was already baked into everything. But honestly, that's a minor hiccup compared to what Franklin got right. The idea that electricity is conserved, that you can't create or destroy it, only move it around, that's a genuinely deep insight. It's one of the foundational principles of physics, and Franklin arrived at it through careful observation and clear thinking, decades before anyone had the mathematical tools to formalize it. But here's the thing about Franklin's era, and really about the entire 18th century when it comes to electricity and magnetism. Everyone was still treating them as completely separate phenomena. You had your electrical people building bigger Leyden jars, doing fancier demonstrations, arguing about whether electrical fluid was one substance or two. And then you had your magnetic people, mostly navigators and compass makers, worrying about declination and dip, and why compass needles sometimes behaved strangely during thunderstorms. That last detail, by the way, is a clue. People had noticed for centuries that lightning could do strange things to compasses. Ships that got struck by lightning sometimes found their compass needles reversed, north suddenly pointing south. Sailors reported this, and it was documented, but nobody quite knew what to make of it. It was treated as a curiosity, a footnote, not as evidence of something profound. Because if you already believe that electricity and magnetism are fundamentally different things, which everyone did, ever since Gilbert had drawn that line back in 1600, then a lightning strike messing with a compass is just weird. It's an anomaly. It's not a doorway to a deeper truth. And so the 18th century rolls on, and electricity gets more sophisticated. You get Charles-Augustin de Coulomb in France in the 1780s, building his beautiful torsion balance, a delicate instrument that could measure incredibly tiny forces, and using it to show that the force between electric charges follows an inverse square law, meaning if you double the distance between two charged objects, the force between them drops to a quarter. That's the same mathematical relationship that Newton found for gravity. Coulomb published this in a series of memoirs between 1785 and 1791, and it was elegant, precise work. He did similar measurements for magnetic poles and found the same inverse square relationship. So now you have electricity following an inverse square law, and magnetism following an inverse square law, and they both look mathematically similar, and yet, everyone still considers them separate forces. The mathematical resemblance was noted, sure, but resemblance isn't identity. Lots of things in physics follow inverse square laws. It doesn't mean they're the same thing. So as the 18th century closes and the 19th begins, you have this situation where electricity and magnetism are both fairly well characterized individually, but the wall between them is still standing. And it's going to take a very specific moment, one experiment really, to knock that wall down. And it happens in Copenhagen in 1820, and the man who does it is Hans Christian Ørsted. Now, Ørsted is a fascinating figure, and he deserves a proper introduction because his story illustrates something important about how scientific breakthroughs actually happen. He was Danish, born in 1777, the son of a pharmacist. He studied pharmacy and then philosophy and then physics, and he was deeply influenced by the German Romantic tradition in philosophy, specifically by the ideas of Friedrich Schelling, who believed that all the forces of nature were fundamentally unified. That nature, at its deepest level, was one thing expressing itself in different ways. This was a philosophical conviction, not a scientific one. There was no experimental evidence for it. But Ørsted believed it, and it shaped the questions he asked. Think about what that means. For over 2,000 years, since Thales, people had looked at electricity and magnetism and seen two separate things. Gilbert had reinforced that separation. Coulomb had characterized them independently. And here comes Ørsted, who walks into the problem already believing they must be connected, because his philosophy tells him that all forces are connected. And that belief, that conviction, is what made him set up the experiment that changed everything. Here's what happened. On April 21st, 1820, Ørsted was giving a lecture to students at the University of Copenhagen. He had a battery. By this point, Alessandro Volta had invented the voltaic pile about 20 years earlier, which was the first real battery, and that's a whole story in itself. But the key point is that by 1820, people had a way to produce a steady, continuous electric current, not just static sparks. So Ørsted had a wire connected to a battery, carrying a current, and he had a compass needle sitting nearby on the table. And during the lecture, he noticed something. When the current was flowing through the wire, the compass needle moved. It deflected. It swung away from pointing north and oriented itself roughly perpendicular to the wire. Now, there's some debate about whether this was truly a surprise to Ørsted, or whether he had been specifically looking for this effect. Some accounts suggest he had been trying the experiment privately for a while and had gotten ambiguous results, and that the lecture demonstration was a more careful attempt. Others paint it as pure serendipity, a chance observation during a routine lecture. The truth is probably somewhere in between. Ørsted had been looking for a connection between electricity and magnetism for years, motivated by his philosophical beliefs. He had tried various configurations and hadn't found anything convincing. But on that day, with a strong enough current and a sensitive enough compass, the effect was clear. And here's what's really important about what he observed. The compass needle didn't point toward the wire or away from it. It pointed around it. The magnetic force created by the electric current wasn't pulling or pushing in a straight line. It was circling the wire. If you imagine looking at the wire end-on, like looking down the barrel of a pipe, the magnetic force wraps around it in a circle. That's completely different from anything anyone had seen before. Gravity pulls things in straight lines toward masses. Electric forces push or pull charges in straight lines toward or away from each other. But this new magnetic effect from a current, it curled. It wrapped around. It was something geometrically new. Ørsted spent the next few months carefully documenting the effect, trying different wire orientations, different current strengths, placing the compass above and below the wire. He published his results in July 1820 in a short Latin pamphlet that he sent to scientific societies across Europe. And the reaction was immediate and electric, if you'll pardon the pun, because this was the first definitive, reproducible experimental proof that electricity and magnetism were connected. After 2,000 years of treating them as separate, someone had finally shown that an electric current produces a magnetic effect. The wall was cracked, and the news spread fast. Within weeks, some of the sharpest minds in European physics were scrambling to understand and extend what Ørsted had found. And this is where the story really accelerates, because in the months and years following Ørsted's discovery, a cascade of breakthroughs happened so quickly, it's almost dizzying. The first major response came from France, from André-Marie Ampère, and Ampère moved with astonishing speed. He heard about Ørsted's result in September 1820, and within a week, a single week, he had begun a series of experiments that would go far beyond what Ørsted had done. Ampère was a mathematical physicist, brilliant and intense, and he had a tragic personal history that's worth a brief detour because it tells you something about the man. His father was guillotined during the French Revolution when Ampère was 18. By some accounts, the shock was so severe that Ampère spent over a year in a kind of stupor, unable to read or work. He eventually recovered, threw himself into mathematics and science, and became one of the most productive physicists of his generation. But there was always a driven, almost desperate quality to his work, as if he was racing against something. So Ampère hears about Ørsted's compass needle, and he immediately asks a question that Ørsted hadn't addressed. If a current-carrying wire produces a magnetic effect, what happens when you put two current-carrying wires next to each other? Do they interact? And the answer is yes, they absolutely do. Ampère showed that two parallel wires carrying current in the same direction attract each other, and two parallel wires carrying current in opposite directions repel each other. This was stunning. You didn't need a magnet at all. Two ordinary wires carrying ordinary currents exert forces on each other. Electricity wasn't just connected to magnetism, it was generating magnetism, and that magnetism was creating real, measurable mechanical forces between conductors. Ampère went further. He developed a mathematical framework to describe these forces, what we now call Ampère's law, and he proposed something truly radical. He suggested that all magnetism, everywhere, is caused by electric currents. A permanent magnet, like a compass needle or a lodestone, isn't fundamentally different from a current-carrying wire. Instead, Ampère proposed, there must be tiny circular currents flowing inside the iron itself at a scale too small to see, and those microscopic currents are what create the magnetic effect. He called them molecular currents. Think about how bold that idea is. He's saying there's no such thing as magnetism as a separate force. There's only electricity, and magnetism is what electricity does when it moves. That's a profound claim, and it turned out to be essentially correct, though the full explanation had to wait for quantum mechanics a century later. The molecular currents Ampère imagined are actually the orbital and spin-angular momentum of electrons within atoms. He had the right picture, just not the right mechanism. But the core insight, that magnetism is a consequence of moving charges, that's one of the deepest truths in all of physics. Meanwhile, also in 1820, a French physicist named Jean-Baptiste Biot and his colleague Félix Savart were doing their own careful measurements of the magnetic field around a current-carrying wire. They worked out the precise mathematical relationship, how the strength of the magnetic effect depends on the current, the distance from the wire, and the geometry of the setup. The result is called the Biot-Savart law, and it's still used today by engineers designing everything from MRI machines to electric motors. It tells you exactly how to calculate the magnetic field produced by any configuration of current-carrying wires, and it's one of those tools that sounds abstract but is profoundly practical. So by the end of 1820, just months after Ørsted's discovery, the landscape of physics had completely changed. Electricity and magnetism were no longer separate. A current produces a magnetic field. Two currents exert forces on each other. And maybe, just maybe, all magnetism everywhere is really just electricity in disguise. That's an incredible amount of progress in a very short time. But notice what's still missing. Everything so far goes in one direction. Electricity produces magnetism. A current makes a compass needle move. But what about the reverse? Can magnetism produce electricity? Can you start with a magnet and somehow get a current to flow? That's the obvious next question, and a lot of people were asking it. Ampere was thinking about it. Ørsted was thinking about it. But the person who would actually crack it, who would demonstrate that magnetism can indeed create electricity, was working in a basement laboratory in London, and he came from a background so unlikely that his story almost doesn't seem real. His name was Michael Faraday, and he might be the most important experimental scientist who ever lived. And I don't say that lightly. Faraday was born in 1791 in Newington Butts, which is now part of South London, into a family that had almost nothing. His father was a blacksmith who was frequently too ill to work. The family was poor, genuinely poor, not romantically poor. Faraday later recalled that there were weeks when he and his siblings shared a single loaf of bread. He received what he called a very basic education: reading, writing, a little arithmetic, and that was it. At 13, he was apprenticed to a bookbinder named George Rebow, and this is where the story takes its turn. Because here's the thing about being a bookbinder's apprentice. You're surrounded by books, and Faraday read them. He read everything that came through the shop, but two works in particular changed his life. One was an entry on electricity in the Encyclopedia Britannica. The other was a book called Conversations on Chemistry by Jane Marcet, which was a popular science book written specifically to make chemistry accessible to people without formal training. Faraday didn't just read these books, he started doing experiments. He built a crude electrostatic generator out of bottles and old wood. He performed simple chemical experiments in the back of the bookbinding shop, and he started attending public lectures at the Royal Institution, which was one of the great scientific venues in London. In 1812, when Faraday was 20, a customer gave him tickets to a series of lectures by Humphrey Davy, who was the most famous chemist in England at the time. Faraday attended the lectures, took meticulous notes, beautiful, detailed notes, bound them into a book, because of course he could do that, and sent them to Davy with a letter asking for a job. Any job. Davy was impressed enough that when a position as laboratory assistant opened up at the Royal Institution in 1813, he hired Faraday. And that was it. That was the door. A bookbinder's apprentice walked into one of the finest scientific laboratories in the world, and he never left. Now, Faraday's early years at the Royal Institution were spent doing chemistry, and he was brilliant at it. He discovered benzene. He liquefied chlorine, He did important work on steel alloys. But the thing that would make him immortal, the thing that connects directly to everything we've been talking about, started in the 1820s, when Faraday turned his attention to the relationship between electricity and magnetism. Remember the question that was hanging in the air after Ørsted and Ampere's work? Electricity produces magnetism. Everyone knew that now. But can magnetism produce electricity? Faraday was obsessed with this question, and he had an advantage that the French and German physicists didn't fully appreciate. He thought in pictures. Faraday had almost no mathematical training. He couldn't read the equations that Ampere and Biot and Savart were writing. But he had an extraordinary ability to visualize physical processes, to imagine what was happening in the space around a wire or a magnet. And this visual, intuitive approach led him to develop one of the most powerful concepts in all of physics, the idea of the field. Let's talk about that for a second, because it matters enormously. Before Faraday, the standard way of thinking about electric and magnetic forces was what physicists call action at a distance. You have two charges. They push or pull on each other across empty space, and that's that. The force just reaches across the gap somehow. Newton's gravity worked the same way. The sun pulls the earth pulls the sun, and nobody worries too much about how the force gets from one to the other. Faraday found this deeply unsatisfying. When he looked at iron filings arranging themselves around a magnet, you've probably seen this, those beautiful curving patterns that fan out from pole to pole. He didn't see a mathematical abstraction. He saw something real. He saw lines of force filling the space around the magnet, and he believed those lines were physically meaningful. The space around a magnet isn't empty. It's filled with something, a condition, a state, a field, and it's that field that carries the force. This was a radical idea. Most of the mathematically trained physicists on the continent thought it was a bit naive, frankly. They had their equations, their inverse square laws, their elegant formalisms, and they didn't need to imagine invisible lines filling up space. But Faraday was right. He was profoundly, fundamentally right, and the concept of the field would eventually become the central idea in all of modern physics. Every force we know about, electromagnetic, gravitational, nuclear, is now understood in terms of fields. Faraday saw it first, and he saw it because he couldn't do the math. That's not a criticism. It's one of the most beautiful ironies in the history of science. His lack of mathematical training forced him to think in physical, spatial, intuitive terms, and that's exactly what the problem required. But anyway, the point is, Faraday was thinking about fields, thinking about lines of force, and thinking about whether magnetism could produce electricity. He tried experiment after experiment throughout the 1820s. He would place a wire near a magnet and look for a current. Nothing. He would wrap a wire around a magnet and connect it to a galvanometer. That's a sensitive instrument for detecting small currents. And watch the needle. Nothing. The magnet just sat there, and no current flowed. And here's what's so tricky about this. The reason it took so long. Faraday was looking for a steady current. He expected that if you put a wire near a magnet, a current would flow continuously, the same way a current flows continuously when you connect a wire to a battery. That seemed like the natural symmetry. Electricity produces a steady magnetic field, so magnetism should produce a steady electric current. Right? Wrong. And that word wrong contains one of the deepest insights in all of electromagnetism. The breakthrough came on August 29, 1831. Faraday had built a device, an iron ring about 6 inches across, with two separate coils of wire wound around it on opposite sides. One coil was connected to a battery. The other was connected to a galvanometer. His idea was that if electricity in the first coil created magnetism, and that magnetism traveled through the iron ring to the second coil, maybe it would create electricity in the second coil. So he connected the battery, and the galvanometer needle jumped. It twitched, and then it settled back to 0. And when he disconnected the battery, the needle jumped again in the opposite direction and then settled back to 0 again. Think about what that means. There was no steady current. The current in the second coil appeared only at the moment of change, when the battery was connected or disconnected, when the magnetic field through the ring was increasing or decreasing. Once the field was stable, even if it was strong, nothing happened. The current only existed during the transition. Faraday had discovered electromagnetic induction, and the key insight, the one that had eluded everyone, was that it's not a magnetic field that produces electricity. It's a changing magnetic field. The change is everything. A static magnet sitting next to a wire does nothing, but move that magnet, push it toward the wire or pull it away, and suddenly a current flows. Stop moving it, and the current stops. It's the motion, the variation, the change in the magnetic field that creates the electric effect. This is Faraday's law of electromagnetic induction, and it's one of the 4 Maxwell's equations that govern all of electromagnetism. We'll get to Maxwell later. That's a whole other story, and what a story it is. But for now, just sit with this idea for a moment. A changing magnetic field creates an electric field, not a static one, a changing one. And the faster the change, the stronger the effect. Faraday spent the rest of 1831 exploring this discovery from every angle. He showed that you could induce a current by moving a magnet in and out of a coil of wire. He showed that spinning a copper disc between the poles of a magnet produced a continuous current. This was the first electric generator, the first dynamo. He showed that the amount of current you induced depended on how quickly you changed the magnetic field and how many loops of wire you used. More loops, more voltage. Faster change, more voltage. He was essentially writing the rules for every electric generator and transformer that would ever be built. And here's the kicker. This is the principle behind virtually all the electricity you use. Right now, tonight, the electricity flowing into whatever device you're listening to this on was almost certainly generated by electromagnetic induction. Somewhere, a turbine is spinning, driven by steam from burning coal or gas or nuclear fission, or by falling water, or by wind. And that spinning turbine is rotating a magnetic field inside coils of wire, and that changing magnetic field is pushing electrons through those wires, creating the current that travels through the grid to your home. The basic mechanism is exactly what Faraday demonstrated in 1831 with his iron ring and his galvanometer. The scale is unimaginably larger, the engineering is vastly more sophisticated, but the principle is identical. A changing magnetic field induces an electric current. That's it. That's where your electricity comes from. Now, Faraday also discovered something else in those experiments, something that would later be formalized by a Russian physicist named Heinrich Lenz. When you induce a current by changing a magnetic field, the induced current itself creates its own magnetic field, and that secondary field always opposes the change that created it. Always. If you push a magnet toward a coil, the induced current creates a field that pushes back against the magnet. If you pull the magnet away, the induced current creates a field that tries to pull it back. It's as if nature is resisting the change, trying to keep things the way they were. This is Lenz's law, and it's really a consequence of conservation of energy. If the induced current helped the change instead of opposing it, you'd get a runaway effect. The current would make the field stronger, which would make the current stronger, which would make the field stronger, and you'd be creating energy from nothing. That can't happen. So the induced effect always fights back. Think about what that feels like in practice. If you've ever tried to push a strong magnet through a copper tube, and if you haven't, it's a wonderful demonstration. The magnet falls slowly, almost as if it's falling through honey. The changing magnetic field as the magnet moves induces currents in the copper, and those currents create fields that oppose the magnet's motion. The magnet isn't touching the copper. There's no friction in the ordinary sense. But the electromagnetic interaction creates a braking force. This is the principle behind eddy current brakes, which are used in some roller coasters, in the braking systems of high-speed trains, and in industrial machinery. No contact, no wear, no brake pads to replace, just a magnet and a conductor, and the invisible hand of Lenz's law slowing things down. So by the early 1830s, Faraday had established the other half of the electricity-magnetism relationship. Ørsted showed that electricity produces magnetism. Faraday showed that magnetism, changing magnetism, produces electricity. The symmetry isn't perfect, and that imperfection is actually deep and important. A steady current makes a steady magnetic field. But a steady magnetic field does not make a steady current. You need change. You need variation in time. That asymmetry would later become one of the cornerstones of Maxwell's equations, and it hints at something even more profound about the nature of electromagnetic waves. But we're not there yet. What we should talk about next is what Faraday did with his concept of fields, because he didn't stop at induction. Through the 1830s and 1840s, he kept pushing, kept experimenting, kept developing his picture of invisible lines of force filling all of space. And in 1845, he made another discovery that stunned the scientific world. He showed that magnetism could rotate the plane of polarized light. This effect, now called Faraday rotation, was the first experimental evidence that light and electromagnetism were somehow connected. Light, that most familiar and mysterious of phenomena, was tangled up with the same forces that made compass needles twitch and iron filings arrange themselves into patterns. Faraday suspected, he wrote about this in his notebooks, that light itself might be a vibration of those very lines of force, an electromagnetic disturbance rippling through space. He didn't have the mathematics to prove it, but someone else did, and he was working in Edinburgh, and his name was James Clerk Maxwell, and what he was about to do with Faraday's intuition would be one of the most breathtaking intellectual achievements in the history of science. Maxwell took Faraday's physical intuition, those invisible lines of force, that deep conviction that fields were real things filling space, and he translated them into the language of mathematics, and in doing so, he didn't just confirm what Faraday suspected. He predicted something entirely new, something nobody had seen coming, something that would reshape civilization. So let's talk about Maxwell, James Clerk. Maxwell was born in Edinburgh in 1831, the same year Faraday discovered electromagnetic induction, which is a coincidence so poetic it almost feels scripted. He grew up in a well-off Scottish family, spent much of his childhood at the family estate in Glenlair in the countryside of Galloway, and from an absurdly young age, he was the kind of kid who drove adults slightly crazy with questions. He wanted to know how everything worked. His mother described him at age 3 constantly asking, "What's the go of that? What does it do?" And if the answer wasn't satisfying enough, he'd follow up with, "But what's the particular go of it?" Which, honestly, is a pretty good description of the scientific method coming from a toddler. His mother died when he was 8, cancer, tragically young, and that loss shaped him deeply. His father, John Clerk Maxwell, was devoted but somewhat eccentric, and young James was initially educated by a tutor who was, by most accounts, terrible. The boy was eventually sent to the Edinburgh Academy, where he arrived wearing homemade clothes his father had designed, shoes with square toes, a tunic with a frilly collar, and the other boys immediately and mercilessly nicknamed him Dafty. He endured the bullying with a kind of quiet stubbornness and eventually won over his classmates by being undeniably, almost unnervingly brilliant. By the time he was 14, he had published his first mathematical paper on the geometry of oval curves, which was presented to the Royal Society of Edinburgh. 14 years old. The paper was read aloud by an adult because the society apparently felt it would be unseemly for a boy to present in person. He went on to the University of Edinburgh and then to Cambridge, where he became a Fellow of Trinity College. And it was during the late 1850s and into the 1860s that he turned his attention to the problem that Faraday had spent decades wrestling with: the nature of electric and magnetic fields. Here's what Maxwell recognized, and this is crucial. By the 1850s, there was a tremendous amount of experimental knowledge about electricity and magnetism. Coulomb had measured the force laws. Ampere had described how currents interact. Faraday had discovered induction. Biot and Savart had quantified the magnetic field around a wire. There were dozens of known relationships, hundreds of experimental results. But there was no unified mathematical framework tying it all together. It was like having 1,000 puzzle pieces scattered on a table with no picture on the box. Maxwell decided to build the picture. He started by taking Faraday's lines of force seriously, not as a metaphor, not as a visualization tool, but as a mathematical reality. Where most physicists on the continent still thought in terms of action at a distance, charges and magnets reaching across empty space to push and pull each other, Maxwell adopted Faraday's view that the space itself was doing something. The fields were the thing. The charges and magnets were sources of the fields, but the fields themselves carried energy, exerted forces, and had their own dynamics. His first major paper on the subject, published in 1855 and 1856, was called On Faraday's Lines of Force. In it, he used an analogy, and this is so beautifully Maxwell. He compared the lines of force to the flow of an incompressible fluid through a porous medium. He wasn't saying that electric fields literally were fluid flows. He was saying the mathematics were analogous, and by borrowing the well-developed math of fluid dynamics, he could describe the behavior of electromagnetic fields with precision. It was a brilliant move, because it gave him equations he could work with while staying true to Faraday's physical picture. Think about what he was doing. Faraday had the intuition, but lacked the mathematical tools. The continental physicists had the mathematics, but were committed to the wrong physical picture: action at a distance. Maxwell bridged the gap. He took the right physics from Faraday and married it to the right mathematics, and the result was something neither could have achieved alone. His second major paper, On Physical Lines of Force, came in 1861 and 1862. And this is where things get truly extraordinary. Maxwell was trying to build a mechanical model of the electromagnetic field. He imagined tiny rotating vortices in space, with idle wheels between them, a kind of elaborate clockwork filling the universe. It sounds bizarre, and honestly, the mechanical model itself was wrong. The universe is not full of tiny gears, but the equations he derived from this model turned out to be profoundly, lastingly, almost miraculously right. Sometimes in science, you can get to the correct destination by a wrong road, and Maxwell's vortex model is one of the most famous examples, and here's where the thunderbolt hits. As Maxwell was working through his equations, making sure they were internally consistent, he noticed a problem. The existing laws, the ones Ampere and Faraday and Gauss had established, were almost consistent, but not quite. There was a mathematical contradiction. Specifically, Ampere's law, as it was understood at the time, worked beautifully for steady currents, but broke down for situations where electric fields were changing over time. The equations weren't balanced. It was like a bookkeeping error in the ledger of nature. Let me try to explain this, because it's one of the most important insights in the history of physics, and it's worth taking slowly. Ampere's law said that magnetic fields are created by electric currents, by charges physically moving through space. And that's true. But Maxwell realized that if that were the whole story, you'd get a mathematical inconsistency. The equations would predict things that violated conservation of charge, which is a bedrock principle. Charge doesn't just appear or disappear. So Maxwell proposed a fix. He said, what if a changing electric field also produces a magnetic field, even when there's no physical current flowing? He called this the displacement current. Now, the name is a bit misleading. It's not really a current in the usual sense, not electrons flowing through a wire. It's the idea that when an electric field is changing in time, the change itself acts as a source of magnetism, just as a real current does. Think about what this means. Faraday had shown that a changing magnetic field produces an electric field. That's electromagnetic induction, the principle behind every generator. Maxwell was now proposing the mirror image. A changing electric field produces a magnetic field. The symmetry that was missing. That asymmetry we talked about earlier, where steady currents make steady magnetic fields, but steady magnetic fields don't make steady electric currents. Maxwell was completing the circle. Not perfectly symmetrically, because there are still differences, but in a deep and beautiful way. Change in one field creates the other. Change in that field creates the first. Back and forth, each one generating the other. And here's the thing that should make the hair on your arms stand up, even if you're half asleep. Maxwell sat down with his completed set of equations, the ones with the displacement current added, and he asked, what happens if you have a region of space with no charges and no currents, just fields? Can the fields sustain themselves? And when he worked through the math, he found that yes, they could. A changing electric field would create a magnetic field, and that changing magnetic field would create an electric field, and this mutual generation would propagate outward through space as a wave. An electromagnetic wave. So Maxwell calculated the speed of this wave. And this is one of the most dramatic moments in the history of science. The speed depended on two constants, the permittivity of free space and the permeability of free space, both of which had been measured in laboratory experiments on electric and magnetic forces. They had nothing to do with light, as far as anyone knew. They were just numbers that told you how strong electric and magnetic forces were in a vacuum. Maxwell plugged them in, did the arithmetic, and got a speed of approximately 310,000 kilometers per second. The measured speed of light at the time was about 314,000 kilometers per second. Maxwell wrote, in one of the most understated bombshells in scientific literature, we can scarcely avoid the inference that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. In other words, light is an electromagnetic wave. Light, the thing that lets you see the world, the thing that warms your skin, the thing that travels from stars across billions of kilometers of void. It's made of electric and magnetic fields oscillating together, leapfrogging through space, each one giving birth to the other exactly as his equations predicted. Take a breath with that. Just let it sit for a moment. For thousands of years, light was one mystery, and magnetism was another, and electricity was a third. And in the space of a few pages of mathematics, Maxwell showed they were all the same thing. One phenomenon, one set of laws. The unification is staggering. Maxwell published his definitive treatment in 1865 in a paper titled A Dynamical Theory of the Electromagnetic Field, and then expanded it further in his 1873 treatise. The final form of his equations, what we now call Maxwell's equations, can be written as 4 compact statements, 4 equations that describe all of classical electromagnetism. Every electric field, every magnetic field, every light wave, every radio signal, every X-ray, every microwave heating your leftovers, all of it flows from those 4 equations. Let me walk through them gently, because even in words, they're beautiful. The first equation, Gauss's law for electricity, says that electric charges are sources of electric field lines. Field lines radiate outward from positive charges and converge inward toward negative charges. The total electric flux through any closed surface is proportional to the charge enclosed inside. Simple, elegant, and it encodes Coulomb's law in the language of fields. The second equation, Gauss's law for magnetism, says that there are no magnetic monopoles, no isolated north or south poles. Every magnetic field line that exits a surface must also enter it somewhere. Magnetic field lines always form closed loops. You can't cut a magnet in half and get a north end without a south end. This is still true today, as far as we know, though some physicists suspect monopoles might exist and keep looking for them. The third equation is Faraday's law, the one we spent so much time on earlier. A changing magnetic field creates a curling electric field. This is induction. This is generators and transformers and the entire electrical grid. The fourth equation is Ampere's law, but with Maxwell's crucial addition, the displacement current. Electric currents and changing electric fields both create curling magnetic fields. This is the equation Maxwell fixed, the one that completed the circle and made electromagnetic waves possible. 4 equations. That's it. And from them, you can derive the behavior of everything from a compass needle to a lightning bolt to the light from a distant galaxy. There's a reason physicists sometimes say that Maxwell's equations are the most important equations in all of physics. Not because they're the most fundamental, quantum mechanics and general relativity go deeper, but because they unified so much, predicted so much, and opened the door to so much of modern technology. But here's what's poignant about this story. Maxwell didn't live to see the full vindication of his work. He died in 1879 at the age of just 48 of abdominal cancer, the same disease that had killed his mother at almost the same age. He died knowing his theory was beautiful and self-consistent, but without definitive experimental proof that electromagnetic waves other than light actually existed. He predicted them. He calculated their properties. But nobody had yet built a device to generate and detect them in a laboratory. That proof would come, and it would come from a physicist working in a modest laboratory in Germany, a man named Heinrich Hertz. and the experiments he conducted in the late 1880s would not only confirm Maxwell's theory, but would accidentally lay the groundwork for something Maxwell never imagined: the entire age of wireless communication. Hertz was working at the University of Karlsruhe, and he had devised a beautifully simple apparatus, a spark gap transmitter, essentially two metal rods with a small gap between them, connected to an induction coil that would build up voltage until a spark jumped across. That spark, that brief, violent discharge, was exactly the kind of rapidly changing current that Maxwell's equations said should radiate electromagnetic waves out into the room, and that's exactly what happened. When the spark jumped, it didn't just make a bright flash and a snapping sound. It sent an invisible ripple racing outward through space at the speed of light. The question was whether Hertz could catch it. His detector was almost absurdly simple: just a loop of wire with its own tiny gap, placed across the room from the transmitter. The idea was that if electromagnetic waves really were spreading outward from that spark, they'd induce a tiny voltage in the loop, enough, maybe, to cause a minuscule spark to jump across the detector's gap. And you have to picture this. Hertz is working in a darkened room, because the sparks he's looking for in the detector are so faint that he needs his eyes fully adjusted to the dark to see them. He fires the transmitter. The main spark cracks across the gap, and then he peers, literally peers, at the little loop of wire across the room, looking for the faintest glimmer of a spark jumping a fraction of a millimeter. And he sees it, a tiny spark, barely there, but unmistakable. That moment, in 1887, is one of the great experimental confirmations in the history of physics. Maxwell had predicted, purely from mathematics, that electromagnetic waves should exist. And here was Hertz, in a lab in Karlsruhe, watching them arrive. He went further too. He didn't just detect the waves. He measured them. He figured out their wavelength by bouncing them off metal sheets and creating standing waves, the same way you can create standing waves on a vibrating string. He measured the distance between nodes, calculated the wavelength, multiplied by the frequency he knew from his transmitter, and got the speed. And the speed was the speed of light, exactly as Maxwell had predicted. Hertz also showed that these waves behaved just like light. They could be reflected off flat surfaces. They could be refracted, bent, when they passed through certain materials. They could be polarized. They were, in every measurable way, the same phenomenon as light, just at a much longer wavelength. Visible light has wavelengths measured in hundreds of nanometers. Hertz's waves had wavelengths measured in meters. But the physics was identical. Maxwell was right. Light was an electromagnetic wave, and there was a whole spectrum of electromagnetic waves out there, most of them invisible to human eyes. Now, here's something wonderfully ironic about Hertz. When people asked him what use these electromagnetic waves might have, he essentially said, none. He saw his work as a confirmation of a beautiful theory, a piece of pure physics. He reportedly told his students that his experiments were of no practical use whatsoever, that they simply demonstrated that Maxwell was correct. He couldn't have been more wrong, of course. Within a decade of his experiments, people were using electromagnetic waves to send messages without wires, and within a few decades, radio, television, radar, and eventually everything from Wi-Fi to cell phones would all trace their lineage directly back to those sparks in that darkened room in Karlsruhe. Hertz died young, too, even younger than Maxwell. He was only 36 when he died in 1894, of a condition that started as severe migraines and progressed to what was likely granulomatosis with polyangiitis, an autoimmune disease. He had barely a half-dozen years of truly productive research, but in those years, he changed the world. And there's a reason the unit of frequency, cycles per second, is called the hertz. Every time you tune a radio to a station measured in megahertz, or your computer's processor runs at gigahertz, you're invoking his name. But let's slow down for a second, because there's something happening during this same period that ties all of this together in a way that's really satisfying. Remember how Faraday discovered that a magnetic field could rotate the plane of polarized light? That was back in 1845, and it was the first real hint that light and electromagnetism were connected. Maxwell then built the theory that explained why light is an electromagnetic wave. Hertz proved it experimentally. But there's another thread running alongside all of this, and it has to do with a question that might seem almost philosophical. What are electric and magnetic fields actually made of? What's doing the waving? For most of the 19th century, physicists assumed there had to be a medium, something physical that electromagnetic waves traveled through, the way sound waves travel through air and water waves travel through water. They called this hypothetical medium the luminiferous ether. The ether, and they took it very seriously. It had to be incredibly rigid to support waves traveling at the speed of light, yet somehow perfectly transparent and weightless, because it couldn't interfere with the motion of planets or anything else. It was a strange thing to believe in when you think about it, this invisible, intangible substance filling all of space. But it seemed like the only way waves could propagate. Waves need a medium. That was just common sense. And this is where Albert Michelson enters the story. Michelson was an American physicist, born in what's now Poland, raised in mining towns in Nevada and California during the Gold Rush era. He was meticulous, obsessive about precision, and he became the world's leading expert in optical measurement. In 1887, the same year Hertz was detecting electromagnetic waves in Karlsruhe, Michelson and his colleague Edward Morley conducted what's now considered one of the most important failed experiments in the history of science. The logic was straightforward. If the Earth is moving through the ether as it orbits the sun, then light traveling in the direction of Earth's motion should be slightly slower relative to us than light traveling perpendicular to that motion. It's like swimming in a river. You swim faster going downstream than upstream, and your speed across the current is somewhere in between. Michelson and Morley built an incredibly sensitive interferometer, a device that splits a beam of light into two perpendicular paths, bounces them off mirrors, and recombines them. If one path took slightly longer than the other because of the ether wind, the recombined beams would be slightly out of phase, and you'd see a shift in the interference pattern. They mounted the whole apparatus on a massive stone slab floating in a pool of mercury, so they could rotate it smoothly without vibration. They measured. They rotated. They measured again. They did it at different times of day, different times of year, when the Earth's velocity through space pointed in different directions. And they found nothing, no shift, no ether wind. The speed of light was the same in every direction, regardless of how the Earth was moving. The ether, if it existed, was completely undetectable. And this wasn't a marginal result. Their instrument was sensitive enough that they should have seen the effect clearly if it were there. This was deeply puzzling. Physicists spent nearly 2 decades trying to explain it away. Hendrik Lorentz and George Fitzgerald independently proposed that maybe objects physically contract in the direction of motion through the ether. that the interferometer arm pointing into the ether wind actually got shorter by exactly the right amount to cancel out the expected time difference. It sounds like a desperate ad hoc fix, and in some ways it was, but the mathematics of it turned out to be surprisingly elegant. Lorentz developed a whole set of transformation equations describing how lengths, times, and electromagnetic fields would change for objects moving through the ether. And here's where it gets really interesting, because those Lorentz transformations, worked out to save the ether, turned out to be exactly the mathematical framework that Einstein would use in 1905 when he threw the ether away entirely. Einstein's special theory of relativity started from two postulates. First, the laws of physics are the same in all inertial reference frames. No experiment you do in a smoothly moving laboratory can tell you your absolute velocity. Second, the speed of light in vacuum is the same for all observers, regardless of how they're moving. That second postulate sounds almost absurd. If you're in a car going 60 miles an hour and you throw a ball forward at 20 miles an hour, someone standing on the sidewalk sees the ball going 80. But light doesn't work that way. If you're in a spaceship going half the speed of light and you shine a flashlight forward, someone standing still doesn't see the light going at 1.5 times the speed of light. They see it going at exactly the speed of light. Always, no matter what. And the reason this matters for our story about electromagnetism is that Einstein's starting point was Maxwell's equations. He was deeply bothered by an asymmetry in the way electromagnetism was being taught and understood. Think about Faraday's law of induction. If you move a magnet toward a coil of wire, you get a current. If you hold the magnet still and move the coil toward the magnet, you also get a current. The observable result is the same. All that matters is the relative motion between the magnet and the coil. But in the physics of the time, these were described as two completely different phenomena. Moving the magnet meant a changing magnetic field was creating an electric field. Moving the coil meant the charges in the wire were experiencing a magnetic force. Same result, different explanation, depending on who you said was really moving. Einstein found this deeply unsatisfying, and his resolution was radical. There is no really moving. There's only relative motion. And Maxwell's equations, properly understood, already contained this truth. So in a beautiful way, electromagnetism led directly to relativity. Maxwell's equations were already relativistically correct. They didn't need to be modified when Einstein came along. Newton's laws of mechanics did need modification, but Maxwell's equations were ahead of their time. They were, in a sense, the first relativistic theory, even though Maxwell himself didn't think of them that way. Think about what that means. The equations that Faraday's intuition inspired and Maxwell's mathematics formalized were so deeply right that they pointed the way toward a revolution in our understanding of space and time itself. Electric fields and magnetic fields aren't really two separate things. They're two aspects of a single entity, the electromagnetic field. And which aspect you see depends on your state of motion. A purely electric field in one reference frame looks like a combination of electric and magnetic fields in another. They're interchangeable, linked by the geometry of space-time. And this brings us to something that was happening in parallel with all of this theoretical revolution, something much more practical, much more tangible, and in many ways just as transformative. Because while physicists were arguing about the ether and Einstein was reimagining space and time, engineers and inventors were taking Hertz's electromagnetic waves and figuring out how to use them. and the person most associated with that leap from laboratory curiosity to world-changing technology is a young Italian named Guglielmo Marconi, who in the mid-1890s started experimenting with wireless telegraphy in his family's attic near Bologna. Marconi wasn't a deep theorist. He probably didn't fully understand Maxwell's equations, and he certainly wasn't trying to test fundamental physics. He was a tinkerer, a practical man with an extraordinary instinct for what would work, and he had read about Hertz's experiments and immediately grasped something that Hertz himself had missed. These invisible waves could carry information across distances where wires couldn't reach, across oceans, to ships at sea. And the story of how he made that happen, the engineering challenges he faced, and the rivalries it sparked, is one of those tales where the line between science and showmanship, between invention and sheer audacity, gets wonderfully blurry. So picture this. Marconi is about 20 years old, and he's set up a crude transmitter in the attic of his family's villa, Villa Grifone, just outside Bologna. His father, Giuseppe, is a wealthy Italian landowner, and his mother, Annie Jameson, is actually from the Jameson whiskey family in Ireland, which turns out to matter more than you'd think, because those Anglo-Irish connections would later open doors for Marconi that pure Italian connections might not have. But we'll get to that. For now, he's up in this attic, and he's essentially recreating Hertz's spark gap apparatus, but with a twist. He's not trying to measure wavelengths or prove Maxwell right. He's trying to send a signal as far as he possibly can. And here's where Marconi's practical genius shows up. He made a key observation early on, one of those things that seems obvious in hindsight, but that the academic physicists had largely overlooked. He noticed that if you connected one terminal of his transmitter to a metal plate raised high in the air and the other terminal to a metal plate buried in the ground, the range of his signals increased dramatically. He'd essentially stumbled onto the antenna, or more precisely, he'd figured out that a tall aerial wire, combined with a good ground connection, was the secret to pushing these waves out over useful distances. Hertz had been working with tabletop equipment in a single room, trying to keep his waves contained so he could study them. Marconi wanted the opposite. He wanted them to go everywhere. By the summer of 1895, he was sending signals across the grounds of the villa, a few hundred meters, then a kilometer, then nearly 2 kilometers. There's a famous story, and it's well documented by the family, that his brother Alfonso would go out into the fields with a receiver, and when he successfully picked up a signal, he'd fire a rifle into the air so Marconi could hear the confirmation from the attic. A gunshot as acknowledgement of an invisible electromagnetic wave. There's something beautifully absurd about that. But Marconi quickly realized that Italy wasn't the place to develop this commercially. He approached the Italian government, and they showed polite but limited interest. So his mother's connections came into play. In early 1896, he packed up his equipment. Some of it reportedly got damaged by customs officials who were suspicious of the strange apparatus, and headed to England. And this was a smart move, because Britain had the world's largest navy, the world's largest merchant fleet, and the world's most extensive telegraph network. If anyone was going to see the value of wireless communication, it was the British. Within months, Marconi was demonstrating his system to officials from the British Post Office and the Royal Navy. William Preece, the chief engineer of the Post Office, became an early champion. By 1897, Marconi had established the Wireless Telegraph and Signal Company, later renamed the Marconi Company, and he was pushing his range further and further. Across the Bristol Channel, across the English Channel, from Dover to Wimereux in France, a distance of about 50 kilometers, in 1899. And here's the thing about Marconi that made him different from a pure inventor working alone in a lab. He understood business. He understood patents. He understood publicity. Every successful demonstration was a media event. He was arguably one of the first technology entrepreneurs in the modern sense. Someone who combined technical skill with marketing instinct and corporate strategy. And this made him enemies, or at least rivals, because there were other people working on wireless telegraphy at the same time, and some of them had legitimate claims to priority. The most notable was Nikola Tesla, who had been lecturing about wireless transmission since the early 1890s and had filed patents that arguably covered some of the same ground. There was also Oliver Lodge in England, who had demonstrated wireless signaling as early as 1894 using a device called a coherer, a tube of metal filings that would clump together when hit by electromagnetic waves, changing its electrical resistance and thus acting as a detector. Lodge was a serious physicist, a fellow of the Royal Society, and he felt with some justification that Marconi was building on work that others had done without sufficient acknowledgement. There was Alexander Popov in Russia, who demonstrated a similar system around the same time, and is still celebrated in Russia as the true inventor of radio. The priority disputes got heated and in some cases lasted decades. But Marconi had something none of these rivals had in equal measure: relentless focus on making the technology work over longer and longer distances and the business acumen to commercialize it. And the challenge of distance was genuinely hard. See, the problem is that electromagnetic waves, like light, travel in straight lines. The Earth is curved. So if you're trying to send a signal from England to, say, North America, the curvature of the Earth should block the signal after a couple hundred kilometers at most. The waves should just shoot off into space in a straight line, right over the horizon. And yet, on December 12th, 1901, Marconi claimed to have received a signal, the Morse code letter S, 3 dots, transmitted from Poldhu in Cornwall, England, all the way to Signal Hill in St. John's, Newfoundland, a distance of about 3,500 kilometers, across the Atlantic Ocean. And this was supposed to be impossible. Now, there's actually been some debate among historians and engineers about whether Marconi really received that signal, or whether he heard what he wanted to hear amid the atmospheric noise. The equipment was crude. He was using a simple coherer and a telephone earpiece, listening for 3 faint clicks. There was no recording, no independent verification at the moment of reception. Some scholars think the first truly confirmed transatlantic signals came in early 1902, when Marconi conducted more rigorous tests aboard the SS Philadelphia. But regardless of whether the December 12th reception was definitive, the broader achievement was real. Within months, transatlantic wireless communication was an established fact. And the reason it worked at all, the reason the signals bent around the curve of the Earth instead of shooting off into space, was something Marconi himself didn't fully understand at the time. It turned out that high in the Earth's atmosphere, roughly 80 to 300 kilometers up, there's a layer of ionized gas, the ionosphere, where solar radiation strips electrons from air molecules, creating a region that's electrically conductive. And this conductive layer acts like a mirror for certain frequencies of radio waves. The waves bounce off the ionosphere, come back down to Earth, bounce off the surface, go back up, and so on, hopping around the curvature of the planet. It's like rolling a ball along the inside of a curved tube. The signal doesn't need a straight line of sight, because the ionosphere and the Earth's surface create a waveguide that channels it around the curve. This was worked out theoretically by Oliver Heaviside in England, and Arthur Kennelly in America, both independently proposing the existence of this reflective layer in 1902, right after Marconi's transatlantic demonstration. But it wasn't confirmed experimentally until the 1920s, when Edward Appleton, who would later win the Nobel Prize for it, used BBC radio transmissions to prove the ionosphere existed by measuring the interference patterns between ground waves and waves reflected from above. Think about what that means for a second. Marconi's greatest achievement, transatlantic wireless, worked because of a feature of the Earth's atmosphere that nobody knew about when he did it. He succeeded partly through skill, partly through stubbornness, and partly through sheer luck. The universe happened to have this reflective layer in just the right place to make long-distance radio possible. If the ionosphere didn't exist, or if it existed at a different altitude, or if it didn't reflect the frequencies Marconi was using, the whole thing would have failed, and the history of communication technology would look very different, and the practical impact was immediate and enormous. The first major use case was exactly what you'd expect: communication with ships at sea. Before wireless, once a ship left port, it was completely cut off from the rest of the world until it reached the next port. If something went wrong, a storm, a collision, a mechanical failure, there was no way to call for help. Marconi's company began installing wireless equipment on ocean liners and training operators, and by the first decade of the 20th century, wireless distress calls were saving lives. The most famous case, of course, is the Titanic. On the night of April 14th, 1912, when the ship struck an iceberg in the North Atlantic, the two Marconi operators on board, Jack Phillips and Harold Bride, sent out distress signals using both the older CQD code and the newer SOS code. The Carpathia, about 93 kilometers away, picked up the signal and steamed toward the sinking ship, ultimately rescuing over 700 survivors. Without wireless, every single person aboard would almost certainly have died. The nearest ship that could have helped would have had no idea anything was wrong until the Titanic simply failed to arrive at its destination. But the Titanic disaster also revealed a problem. The Californian, another ship, was actually much closer to the Titanic, possibly close enough to have saved many more lives, but its wireless operator had gone to bed for the night. There was no requirement to maintain a continuous radio watch. After the disaster, regulations changed. The Radio Act of 1912 in the United States and similar international agreements mandated 24-hour radio watches on large vessels, required ships to have backup power for their wireless equipment, and established distress frequencies that had to be kept clear. This is a pattern you see over and over in engineering history. Tragedy driving regulation. Regulation driving better engineering. Better engineering enabling new possibilities that create new risks, which eventually lead to new tragedies and new regulations. It's a cycle, and wireless communication went through it rapidly in its early decades. Now, everything we've been talking about so far, Marconi's wireless telegraphy, ship-to-shore communication, the Titanic, all of this was using electromagnetic waves to transmit Morse code, dots and dashes, on and off. It was digital in a sense, long before anyone used that word. But the next leap was figuring out how to put actual sound onto those waves. Voice, music, continuous audio. And that required a different approach, because you can't just turn a wave on and off to represent the continuous variations of a human voice. You need to somehow shape the wave, mold it, make it carry the pattern of the sound itself. And the technique that made this possible, amplitude modulation or AM radio, is one of those ideas that's so elegant, so beautifully simple, that once you understand it, you'll never hear a radio the same way again. So here's the core idea. Imagine you have a pure electromagnetic wave, a carrier wave people call it, oscillating at some high frequency, say 500 kilohertz. That's 500,000 cycles per second. Way too fast for your ear to hear, way too fast to correspond to any musical note or spoken word. It's just a steady, unwavering hum of electromagnetic energy radiating out from an antenna. By itself, it carries no information. It's like a blank page, present, but empty. Now imagine you have a sound wave, someone's voice, let's say. Sound waves are pressure variations in air, and they oscillate much more slowly, a few hundred hertz for a low voice, a few thousand hertz for higher-pitched sounds. The pattern of those oscillations is complex and constantly changing, because that's what makes a voice sound like a voice, what makes a violin sound different from a trumpet. The shape of the wave, its waveform, is the information. The trick of amplitude modulation is this. You take that high-frequency carrier wave and you vary its amplitude, its height, its strength, in exact correspondence with the pattern of the sound wave. When the sound wave peaks, the carrier wave gets taller. When the sound wave dips, the carrier wave gets shorter. The carrier wave is still oscillating at 500 kilohertz, still cycling away at that same rapid frequency. But now its envelope, the outline traced by its peaks, mirrors the shape of the audio signal. You've impressed the sound onto the wave. You've modulated it. And here's what's clever. At the receiving end, you just need a circuit that strips away the high-frequency carrier and extracts that slowly varying envelope. What you're left with is an electrical signal that matches the original sound wave. Feed it to a speaker, and you hear the voice. The carrier wave was just the vehicle, the delivery truck. The cargo was the pattern of amplitude variations riding along on top of it. Now, the person most often credited with making this practical was a Canadian-born engineer named Reginald Fessenden. And Fessenden is one of those figures in engineering history who was brilliant, visionary, and almost impossible to work with. He was tall, imposing, opinionated, and he burned through partnerships and employers the way some people go through socks. But he saw something that almost nobody else saw at the turn of the 20th century. He saw that the future of wireless wasn't dots and dashes. It was continuous waves carrying continuous sound. The problem was that the transmitters of Marconi's era, spark gap transmitters, produced bursts of electromagnetic energy. They were great for Morse code, for those sharp on-off pulses, but they generated waves across a broad, messy range of frequencies. You couldn't modulate a spark gap signal cleanly because there was no clean, steady carrier wave to modulate. Fessenden realized he needed a transmitter that produced a pure, continuous wave at a single frequency. And that was a much harder engineering problem in 1900. He tried various approaches. He worked with a high-frequency alternator, basically a dynamo spinning fast enough to generate alternating current at radio frequencies. He commissioned the General Electric Company to build one, and the engineer who took on the project was a Swedish-born wizard named Ernst Alexanderson. The Alexanderson alternator was a remarkable piece of machinery, a generator spinning at tremendous speed, producing a steady, continuous radio frequency signal that could then be modulated with an audio signal. It took years to develop. Fessenden was impatient. Alexanderson was methodical. But by late 1906, they had a working system. And on Christmas Eve, 1906, Fessenden did something extraordinary. From a transmitting station at Brant Rock, Massachusetts, He broadcast what is generally considered the first audio-radio broadcast in history. Ship wireless operators up and down the Atlantic coast, accustomed to hearing nothing but Morse code through their headphones, suddenly heard a human voice. Fessenden played a phonograph recording of Handel's Largo. He played O Holy Night on the violin himself. He was apparently a decent violinist, and he read a passage from the Bible. Then he wished everyone a Merry Christmas. Think about what that must have felt like. You're a wireless operator on a ship. It's Christmas Eve. You're sitting in a small room with your headphones on, listening to the usual static and dots and dashes, and suddenly there's music. A violin, a human voice speaking to you. It would have been eerie and magical in equal measure. The ocean is dark around you. The ship is rolling, and sound is coming from nowhere, carried on invisible waves across miles of open water. Now, Fessenden's broadcasts were demonstrations, not regular programming. The technology wasn't ready for mass adoption yet. The Alexanderson alternator was expensive and complex, and the receivers of the day weren't well suited to picking up and demodulating AM signals with any fidelity. What really unlocked broadcast radio was a different technology, the vacuum tube, and specifically the audione tube developed by Lee DeForest. DeForest is another complicated figure. He called himself the father of radio, which irritated pretty much everyone else in the field. He was a self-promoter, sometimes reckless with the truth about his own contributions, and he was involved in a stock fraud scandal that nearly landed him in prison. But the audione tube, which he patented in 1906, the same year as Fessenden's broadcast, was genuinely revolutionary, even though DeForest himself didn't fully understand why it worked. The audione was a triode, a vacuum tube with three elements: a heated filament that emitted electrons, a plate that collected them, and a grid in between. By applying a small varying voltage to the grid, you could control a much larger current flowing from filament to plate. It was an amplifier, a tiny signal in, a much bigger signal out. And this was exactly what radio needed. You could use it to amplify weak incoming radio signals so they could drive a speaker instead of requiring headphones. You could use it to generate continuous oscillations for transmission. You could use it to modulate and demodulate AM signals. The vacuum tube was the Swiss Army knife of early electronics. It was actually Edwin Howard Armstrong, a brilliant and ultimately tragic engineer who figured out exactly how to use the triode to its full potential. Armstrong, while still an undergraduate at Columbia University around 1912, developed the regenerative circuit, a feedback loop that took the output of a triode and fed a portion of it back to the input, dramatically increasing amplification. It was an elegant insight, and it made practical radio receivers possible. Armstrong went on to develop the superheterodyne receiver during World War I, which became the standard architecture for radio receivers for decades, and later he invented frequency modulation, FM radio, which we'll come back to. But here's the thing about AM radio that connects back to everything we've been talking about since Maxwell. When you modulate a carrier wave with an audio signal, you're not just transmitting at one frequency anymore. The mathematics, and this is Fourier analysis, which had been around since the early 1800s, shows that an amplitude-modulated signal actually occupies a band of frequencies centered on the carrier frequency. If your carrier is at 500 kilohertz and your audio signal contains frequencies up to 5 kilohertz, your transmitted signal spreads from 495 to 505 kilohertz. It has a bandwidth of 10 kilohertz, and this is why you can have multiple radio stations in the same city without them all talking over each other. Each station is assigned a different carrier frequency, spaced far enough apart that their sidebands don't overlap. The electromagnetic spectrum, which Maxwell showed was this vast continuum of possible wave frequencies, suddenly became real estate, valuable real estate. And just like land, people started fighting over it. By the early 1920s, commercial radio broadcasting exploded. Station KDKA in Pittsburgh is often cited as the first commercially licensed broadcast station in the United States, going on air in November 1920 with coverage of the Harding-Cox presidential election results. Within 2 years, there were over 500 stations broadcasting in America alone. People bought radio receivers for their homes, big wooden cabinets with glowing vacuum tubes, and families gathered around them in the evening the way they'd later gather around televisions. Radio became the first true mass medium, the first technology that could put the same voice, the same music, the same news into millions of homes simultaneously. And all of it, every bit of it, rested on Maxwell's equations, the carrier wave obeying the wave equation, the antenna radiating because accelerating charges produce electromagnetic fields, just as Maxwell and Hertz had shown, the tuning circuit in the receiver selecting one frequency out of the crowded spectrum because of the resonance behavior of inductors and capacitors, components whose behavior Faraday and Henry had first explored decades earlier. Every layer of the technology was built on the physics we've been tracing through this whole story. But AM had limitations. The biggest one was noise. Because AM encodes information in the amplitude of the wave, anything that affects the amplitude, lightning, electrical interference from motors and engines, atmospheric disturbances, gets mixed right into the signal. That's why AM radio crackles during thunderstorms. The noise is amplitude variation, and the receiver can't tell the difference between intentional modulation and accidental modulation. The signal and the noise live in the same dimension of the wave. Armstrong saw this problem clearly, and his solution was frequency modulation, FM. Instead of varying the amplitude of the carrier wave, you keep the amplitude constant and vary the frequency. When the audio signal peaks, the carrier frequency shifts slightly higher. When it dips, the frequency shifts slightly lower. The information is encoded in how fast the wave oscillates, not how tall it is. And since most natural and man-made noise affects amplitude rather than frequency, an FM receiver can simply clip off all amplitude variations, just flatten them out, and the signal underneath comes through clean. The result is dramatically better sound quality, which is why FM became the home of music radio, while AM carried talk and news. But Armstrong's story doesn't end happily. He patented wideband FM in 1933, demonstrated it convincingly, and spent the rest of his life fighting to get it adopted against the entrenched interests of the AM broadcasting industry and, ironically, against his former friend David Sarnoff, the head of RCA. Sarnoff had once supported Armstrong, but turned against FM when it threatened RCA's AM empire. The FCC moved FM to a different frequency band in 1945, rendering 500,000 existing FM receivers obsolete and forcing Armstrong's experimental station off the air. Patent battles dragged on for years. Armstrong, exhausted and financially ruined, took his own life in January 1954. His wife, Marion, continued the legal fight and eventually won every single patent case, but Edwin never saw it. It's one of the saddest stories in engineering history, and it's a reminder that the path from a brilliant idea to widespread adoption isn't just about physics and engineering. It's about money, politics, corporate power, and human stubbornness. The electromagnetic waves don't care about any of that. They propagate according to Maxwell's equations, regardless of who holds the patent. But the systems we build around those waves, the infrastructure, the regulations, the business models, those are deeply human and deeply messy. And speaking of systems built around electromagnetic waves, there's another thread we should follow. Because while radio was transforming communication and entertainment, a parallel revolution was happening in how we understood the electromagnetic field itself at the smallest scales. Because Maxwell's equations, as magnificent as they are, turned out to be not quite the whole story. There was something happening with light and matter. Something that had been lurking in the background since Hertz first noticed that ultraviolet light falling on his spark gap made the sparks easier to produce. He noted it, published it, and moved on. But that tiny observation, the photoelectric effect, was a crack in the foundation of classical electromagnetism, and when someone finally looked at it closely enough, the whole edifice started to shift in ways nobody expected. So let's talk about what was so troubling. By the late 1890s, physicists had a pretty good handle on what the photoelectric effect looked like experimentally. You shine light on a metal surface, and electrons come flying off. That part made sense in a vague way. Light carries energy. The energy knocks electrons loose. Fine. But here's the thing that didn't make sense at all. If light were purely a wave, the way Maxwell's equations described it, then the energy delivered to the surface should depend on the intensity of the light. Brighter light means a bigger wave, more energy per second hitting the metal. And so you'd expect that if you turned up the brightness, the electrons would come off faster, with more kinetic energy. And if you dimmed the light way down, you'd expect the electrons to trickle out slowly, maybe after a delay, while enough energy accumulated to knock one free. That's not what happened, not even close. What experimenters found, and the German physicist Philipp Lenard did the most careful work on this around 1902, was that the energy of the ejected electrons didn't depend on brightness at all. It depended on the color of the light, on the frequency. Shine dim ultraviolet light on the metal, and electrons popped off immediately with significant energy. Shine the brightest, most intense red light you could produce, and nothing. No electrons at all. Zero. You could blast that surface with red light all day long, and not a single electron would budge. But the faintest whiff of ultraviolet, and out they came, instantly, no delay whatsoever. Think about what that means if you're a classical physicist in 1902. Your wave theory says energy is spread continuously across the wavefront. A dim light is just a small amplitude wave, and it should still eventually deliver enough energy to free an electron if you wait long enough. But there was no waiting. Either the frequency was high enough and electrons appeared immediately, or it wasn't, and they never appeared at all, regardless of intensity. The only thing brightness affected was how many electrons came off, not how energetic each individual electron was. This was deeply weird. And it sat there, this unexplained puzzle, alongside another problem that had been tormenting physicists. The so-called black body radiation problem, where classical theory predicted that a hot object should radiate infinite energy at high frequencies, which was obviously absurd. In 1900, Max Planck had found a mathematical fix for the black body problem by assuming, almost as a trick, that energy could only be emitted or absorbed in discrete chunks, quanta, proportional to the frequency. He didn't fully believe it himself. He called it an act of desperation, but the math worked perfectly. And then, in 1905, The same miraculous year Einstein published Special Relativity, he wrote another paper. And this one, the one about the photoelectric effect, is actually the paper that won him the Nobel Prize, not relativity. In it, Einstein took Planck's idea seriously, more seriously than Planck himself had. Einstein proposed that light isn't just emitted and absorbed in quanta, it actually travels as quanta. Each particle of light, which we now call a photon, carries an energy equal to Planck's constant times the frequency. That's it. One simple relationship. Energy equals h times F. And suddenly, the photoelectric effect made perfect sense. Each photon is a little packet of energy, and the amount of energy in that packet depends only on the frequency. A single ultraviolet photon has enough energy to knock an electron free. A red photon doesn't, no matter how many red photons you throw at the surface. 100 million red photons still can't do what one ultraviolet photon can, because each interaction is one photon hitting one electron. It's not about accumulating wave energy over time. It's about whether each individual packet has enough punch. Here's what's wild about this. Maxwell's equations, those beautiful, complete, magnificent equations that unified electricity, magnetism, and light, they describe light as a wave. And they're right. Light diffracts, it interferes, it polarizes, it does all the things waves do. But Einstein was now saying, light is also made of particles, not instead of being a wave. Also, both at the same time. This wasn't a contradiction that could be resolved by picking one side. Nature was insisting on both. And this is where electromagnetism starts to touch something much deeper, something that would eventually become quantum mechanics, and then quantum electrodynamics. And honestly, we could follow this thread for hours, but let me just sketch the shape of it for you, because it's one of the most beautiful intellectual journeys in all of science, and it grows directly out of everything we've been talking about. Over the next 2 decades, physicists like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others built an entirely new framework for understanding the subatomic world, and electromagnetic interactions were at the heart of it. Every time an electron jumps between energy levels in an atom, it emits or absorbs a photon. Every chemical bond, every color you see, every signal in your nervous system, it's all electromagnetic interactions happening at the quantum level. The classical Maxwell equations emerge as a large-scale average of trillions upon trillions of these tiny quantum events. They're not wrong. They're an extraordinarily good approximation of what happens when you zoom out far enough that the graininess of individual photons smooths into a continuous wave. By the late 1940s, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga independently developed quantum electrodynamics, QED, which is the full quantum theory of how light and matter interact. And QED is, by some measures, the most precisely tested theory in all of science. Its predictions match experiments to something like 10 decimal places. Imagine predicting the distance from New York to Los Angeles and being accurate to the width of a human hair. That's the kind of precision we're talking about. And the core of QED is still electromagnetism. It's still about charged particles and photons. It's still, at its root, about the same force that made amber attract straw in ancient Greece, the same force that deflected Ørsted's compass needle, the same force that Faraday saw spinning a wire around a magnet, the same force Maxwell captured in 4 equations. It's just that now we understand that force at a deeper level, as an exchange of virtual photons between charged particles, a constant quantum conversation happening everywhere, all the time. in every atom of your body. So let's come back up for air and think about where we've traveled tonight. We started with the ancient Greeks rubbing amber and noticing something strange. We watched as, for nearly 2,000 years, electricity and magnetism seemed like separate curiosities, parlor tricks, compass needles, Leyden jars. Then, in the span of about 80 years, from Ørsted's 1820 discovery through Einstein's 1905 papers, the entire picture transformed. Electricity and magnetism turned out to be the same force. That force turned out to propagate as waves. Those waves turned out to be light itself. Light turned out to travel at the same speed for everyone, reshaping our understanding of space and time. And then light turned out to be both wave and particle, opening the door to quantum mechanics. Each step seemed impossible until someone took it. Each breakthrough was built on the last. And the people who made those breakthroughs, they were real, complicated, sometimes difficult human beings. Faraday, the bookbinder's apprentice who couldn't do advanced math but could see fields in his mind more clearly than anyone. Maxwell, the quiet Scottish genius who translated Faraday's visions into the language of calculus and changed physics forever, then died at 48. Hertz, who proved Maxwell right and died at 36, never knowing that his waves would carry music and voices and pictures around the world. Armstrong, who gave us FM radio and super heterodyne receivers and was destroyed by corporate politics. Einstein, who started as a patent clerk and reimagined the universe. These stories matter. They're not just biographical footnotes. They tell you something essential about how understanding actually advances, not in smooth, logical steps, but in lurches and stumbles and arguments and occasional flashes of insight that seem to come from nowhere. Faraday didn't need to know Maxwell's equations to discover induction. Maxwell didn't need to detect radio waves to predict them. Einstein didn't need experimental evidence of time dilation to derive special relativity from two simple postulates. Sometimes the math leads, sometimes the experiment leads, sometimes pure physical intuition leads, and the others catch up later. And here's something I find deeply comforting about all of this, especially at this hour, when you're lying there in the dark. The electromagnetic field is everywhere around you right now. It's in the light that came through your windows today, in the radio waves passing through the walls, in the infrared radiation your own body is gently emitting as heat. The phone you might have set on your nightstand is full of circuits where electrons are responding to electromagnetic forces billions of times per second. The chemical reactions keeping your cells alive are governed by electromagnetic interactions between atoms. The neurons in your brain, even now, are firing tiny electrical signals, ions flowing through channels, generating minuscule magnetic fields. You are, in a very real sense, an electromagnetic being living in an electromagnetic universe. Every color you've ever seen is a different frequency of electromagnetic wave hitting the photoreceptors in your eyes. Every sound you've ever heard started as a pressure wave in the air, but was converted to electrical signals in your ear. Every thought you've ever had involved electromagnetic forces holding molecules together and pushing electrons around. Maxwell's equations are running right now, in the walls of your room, in the wiring behind the outlets, in the starlight that's falling on the roof above you. The same equations, the same four relationships between electric and magnetic fields that a Scottish physicist wrote down in the 1860s. They haven't changed. They haven't needed updating at the classical scale. They just quietly, faithfully describe how fields move and interact, the way they always have, the way they always will. And the waves those equations describe, they're out there right now too. Radio waves from stations hundreds of miles away are passing through your body this very second. Cosmic microwave background radiation, the faint afterglow of the Big Bang itself, is washing over you. Light from stars that burned out before the Earth existed is still traveling through space, still obeying Maxwell's equations, still carrying energy and information across the void at exactly 299,792,458 meters per second. There's something quietly magnificent about that, about the idea that the same physics governs the spark from a wool sweater and the light from a galaxy 10 billion light years away. That a force first noticed because amber picked up bits of straw turned out to be the force that holds atoms together, carries information across oceans, lights up cities, and lets you see the face of someone you love. So, as you drift off, let that settle in. The electromagnetic field is the invisible architecture of almost everything you experience. It was here before anyone understood it, and it'll be here long after. Faraday imagined it, Maxwell described it, Hertz proved it, and now you know a little bit about how it all fits together. The charges and the currents, the fields and the waves, the particles and the quanta. It's one long, unbroken story, stretching from a piece of amber in an ancient Greek's hand to the photons gently radiating from your own skin as you lie here, warm and still, in the dark. And that's enough for tonight. The equations will still be there in the morning. The waves will still be traveling. The field will still be humming along, quiet and everywhere, doing what it's always done. You don't need to hold on to any of this. Just let it go, let it settle, and sleep.